Hello, my name is Jessica Reed, and I am a geologist with the U.S. Geological Survey Earthquake Science Center in Menlo Park, California. Today, I'm very pleased to talk with you about the basics of liquefaction, and in particular, I want to talk about the relationship between flow liquefaction and landslides. We know that some landslides can be much more destructive than others. And this image right here is before an extremely destructive landslide that occurred in the town of Yungay. In front of you are the Huascaran Mountains and Yungay before the landslide. And this shows afterwards. So this was May of 1970, quite a while ago. An earthquake of magnitude 7.9 occurred off the coast of Peru, and it triggered a failure on the Nevado Huascaran, which quickly developed into a debris avalanche and mud flow. Mud flows, flow slides, and debris avalanche flows, also known as DAFs, like the one that you see here on the right, they're fast and they're expansive and they're extremely destructive kinds of mass movements. And this landslide was not an exception. It flowed extremely quickly from the mountain to the town of Yungay, causing the deaths of more than 18,000 people. It exhibited extremely high velocity with an average of around 280 kilometers per hour. And it flowed quite a long ways, showing a high mobility. One mechanism that can cause landslides to accelerate dramatically this way and transport material such long distances is called liquefaction. Liquefaction, like pretty much everything, has been defined a few different ways. One very intimidating, in my opinion, definition is all phenomena involving excessive deformations or movements as a result of transient or repeated disturbance of saturated, cohesionless soils. Basically, in plainer language, liquefaction is simply when a solid soil behaves as a liquid would. Some soils can be more susceptible to that liquefaction than other soils. For example, loose, well-saturated soils that have homogeneous grain size and few fines, much like the cartoon here you see, all of the grains are the same size and well-rounded too, which helps, and have very large pore spaces. The pore space is maximized, and that's very important for liquefaction initiation, and they're filled with water. These characteristics are more common in younger deposits that haven't been compacted and are frequently volcanic or sandy deposits. Also, areas that have experienced liquefaction in the past are very likely to do so again, and that's often taken into account in liquefaction susceptibility assessments. So let's go over the basics of soil strength and liquefaction initiation. First, you would have an effective stress, which is simply a result of gravity and the normal forces of grains resting on one another. And this gives the soil its strength. The effective stress works against minor shear stresses, allowing the soil to remain relatively stable. Then you would have a pore fluid, shown in blue here, and the pressure that it exerts on the grains containing it. The pore pressure ratio is the relationship between the effective stress and the pore pressure. In order for the soil to remain stable, the pore pressure must be less than the effective stress. Once the pore pressure is equal to or greater than the effective stress, the pore pressure ratio equals 1, and the strength of the soil is compromised. And that's when liquefaction would occur. So we can take a look at a basic cartoon of this process. You would start out with a well-saturated sediment with water in the pore space, which is very large. And then for flow liquefaction, which is what we're talking about today, a single shear force would be introduced. This could be an added mass somewhere, an earthquake, a storm wave, machinery, or the weight of a landslide, which we'll talk about later. When the shear stress is introduced, the grains will rearrange themselves and pore space is decreased as the stacking becomes more efficient. If the material, but we will have the same amount of water in this situation, and that means that the pore pressure will increase. If the material has been sheared quickly enough, this water won't have a chance to escape and the sediment will be suspended. Effective stress will be reduced to zero as the grains can no longer, they're no longer touching. It's important to remember that in the case of flow liquefaction, this would only occur if the initial shear stress is greater than the strength of the material. And this can occur if the duration or the amplitude is great enough. But in the end, this sheared suspended grains would have very little resistance to further shearing. In 2014, an enormous landslide occurred in Oso, Washington, in the United States. This event has been very carefully studied and mapped and is therefore a useful example for the study of liquefaction and also hydroclimatically triggered landslides. It was March 22nd, 2014, an enormous landslide of about 8 million cubic meters of material destroyed more than 40 structures and killed 43 people. In some areas, the landslide deposits were as deep as 20 meters. The region has a history of large landslides, as you can see. This is a figure showing various landslides that have occurred in the last 14,000 years. The letters and the colors indicate age, so you would have red and the letter A indicate the most recent slide, which is the one from 2014, and orange is a little bit less recent, and yellow would be longer ago in the past. It's also important to know that a large part of the landslide deposits here were sand and glacial till, which are perfect ingredients for liquefaction. You can see here that the slide was large enough to cover the floodplain and actually dam up the river for some time. Here the landslide is outlined in yellow, and a cross section is given from X to X prime and shown below. There is some vertical exaggeration, but not much. This landslide, you can see, traveled horizontally much further than its vertical displacement. This is actually an index called landslide mobility, which is commonly used to characterize landslides, particularly high-speed landslides such as this one. The length over height ratio of displacement here was about 9.5, which means that this landslide exhibited a very high mobility. Um, Another measure that people use is the slope, and the slope here was less than 20 degrees. Liquefaction can cause the kind of high mobility that we do see in Oso. So some researchers, Iverson et al., created a model to explore the possibility that liquefaction was involved in this landslide and caused the high mobility. So I'm going to show you a nice video of the simulations that they created. I'll just point out first that the variable m is the initial, or is the solid volume fraction, which is actually the inverse of porosity.
A large destructive landslide occurred near Oso, Washington on March 22, 2014. Computer simulations indicate that it could have behaved very differently, with much less mobility and destructiveness, if the ground had been less porous and water saturated. Results of two simulations follow. The first simulation shows computed landslide behavior that best matches that observed at Oso. The landslide accelerates rapidly after slope failure occurs because the porous, water-saturated ground liquefies after it fails. Values of the parameters m0 and mcrit determine how sediment porosity changes during the early stages of landslide motion. Here, with m0 slightly smaller than mcrit, pore space declines, causing increased pore water pressure and decreased friction. As a result, a liquefied high-speed landslide crosses the 1 kilometer wide river floodplain in about 1 minute. An alternative simulation shows landslide behavior that could have occurred if the water-saturated ground had been slightly less porous. In this case, the failing ground does not liquefy. The resulting landslide moves relatively slowly and stops after it travels only about 100 meters. If the values of m0 and mcrit are equal, as they are in this simulation, then porosity reduction does not occur during landsliding. As a consequence, pore water pressures do not increase and landslide friction remains high. Further details on this work can be found in the publication listed here.
So we can take a look at some of those frames. The top row would show time at 60 seconds and then 600 seconds in the bottom row. And they discovered that when the initial solid volume fraction is less than the static critical state volume fraction, which is the case on the right, you can see by the negative difference here, it indicates a change in porosity, and some contraction of sediment occurred, which would decrease the pore space, increasing pore pressure, and causing liquefaction, which would dramatically increase the mobility of the landslide, according to the simulation. You can see the large difference between time at 60 seconds and time at 600 seconds, and even from, this is t equals 0, which is the same for both of their models, the difference between that and the right-hand side of t equals 60 seconds. On the other hand, when the initial solid volume fraction is equal to the static critical state volume fraction, right here on the left, it means that no sediment contraction occurred, and the resulting model shows a much lower mobility than the model on the right. This is what the researchers found, and it's a pretty convincing argument, that while the landslide was triggered by heavy rainfall, what made this particular landslide so destructive was the high mobility, which was caused by basal liquefaction when the upper parts of the landslide exerted shear on the base. Of course, liquefaction also requires saturated soil, and rainfall was an important part of the liquefaction as well as the landslide triggering. So, to sort of sum up, in the Oso, Washington uh, case and in flow liquefaction, you would have wet, loose sediment with a high porosity, and it's compacted at the landslide base during landslide failure, which would cause a sudden increase in pore pressure, decrease in shear strength, and liquefaction, and possibly sustained liquefaction if the material continues to move rapidly. So the observations and models made from the Oso, Washington landslide could also serve as useful comparisons to other landslides, including especially landslides in Indonesia. Many parts of Indonesia experience heavy rainfall and frequent landslides due to steep slopes and unconsolidated and often volcanic sediment, and can be triggered by active tectonism in the area. Additionally, many people in Indonesia live in zones that are vulnerable to landslides, which adds urgency to the research. On December 13th, 2014, actually the same year as the Oso landslide, a devastating landslide occurred in central Java. A steep slope, which you can see here, and heavy rain contributed to the mud flow you see, which caused the deaths of 93 people. As we continue to learn about these relationships between slope failure and its relationship to measurable conditions like rainfall and soil properties, we are improving our ability to gauge these risks of landslides and flow liquefaction for a given time and area. And flow liquefaction often occurs in landslides which are caused by excess rainfall. And landslide early warning systems based on rainfall observations and predictions is particularly relevant. Landslide early warning systems often include analyses that are also used to determine liquefaction susceptibility, including slope stability, soil properties, and precipitation. The landslide early warning system established in Indonesia has been operational since the end of 2017. It was established by the BLS, and it continues to provide landslide hazard warnings. It provides them twice a week with a forecast of 4 days. It uses data from observed precipitation data and daily precipitation forecasts from satellite, a map of landslide prone areas, rainfall threshold area seen in this graph on the top right, soil properties data for slope stability analyses seen in this lighter brown box on the right. This graph for rainfall threshold on the top right shows the precipitation threshold employed for this landslide early warning system in Indonesia. It is the median of cumulative precipitation data for 83 observed landslides that were induced by rainfall. The numbers were selected, so for number of days before a landslide, it's 61 is the median here, and 91 is the median for 3 days. And they were selected for data from Java, but incoming data pending, the observations will expand to include other parts of Indonesia that might have different rainfall patterns. So here is the landslide prone map, and the orange areas have a moderate high, and the red areas have a very high landslide prone value. And warning signals will be issued in these areas, just the orange and red, if the precipitation threshold seen on this previous slide here is met or exceeded. And then that would trigger a slope stability analysis based on soil properties. And these landslide early warning systems are still young and constantly being improved. So just to sum up a little bit, we engaged with the topic of liquefaction and the very basics. We learned about susceptibility, the soil characteristics that would promote liquefaction, the importance of pore space and pore pressure, and the importance of water and a saturated soil. We talked about the amplitude or duration of the loading exceeding the strength of the undrained soil in order to trigger liquefaction, and the relationships between landslide mobility and basal liquefaction in rainfall-induced landslides. And finally, we did a quick overview of hazard mitigation techniques and the status of landslide mitigation today.